In this video, I'm going to use Wolfram-Cloud Mathematica to look at some of the properties and do a simulation of a problem that has a negative binomial probability distribution. Okay, so this is an extension of the geometric probability distribution. And in the geometric probability distribution, I want to ask the question, I have something, I'm going to call it a try. So there's something I'm going to try to do. And then there will be a result I'll say I want. I'll call it a success. It might be something that I don't want, but just for simplification of vocabulary, we'll call it a success. And then so there's some probability P of success, and therefore 1 minus P probability of failure. And then in a geometric distribution, you'll want to know, is the X try my first success? Okay, so did I, so I'm rolling, say I'm rolling a die, and I want to know, did I get a 5? So, how many times did I roll it until I got 5 for the first time? So in the negative binomial distribution, it's just an extension of that. And you're looking for, so if you say that thing that stopped you was your success, then you're looking for not your first success, but your, we'll say, rth success. So we'll say I want R successes. Okay. So now, if it's the X try that gives you your rth success, then that last one is, we know it was the last one and we know it was a success. So we're going to pull that out. And now we're looking for sort of the probability for there to be R minus 1 successes distributed among X minus 1 tries. So we're going to take away 1 try and 1 success because that is the very last one. And so then we're looking for X minus 1 things, R minus 1 things distributed among X minus 1 things. And so that's where the binomial comes in. And that's giving it its name of the negative binomial distribution. Okay, so the probability of one of these things, if I knew the first success was on the third try, etc., if I knew sort of specific locations and asked the probability of that, altogether that's going to be P to the R minus 1 for R minus 1 successes, and then I'm going to add in my last success, so I'll make it P to the R, and then 1 minus P to the X minus R. But then the number of ways we can do that, that's where the binomial comes in, and that's the binomial of X minus 1, R minus 1. Okay, and that is, the binomial is just factorials, so it's like the binomial of nm would be n factorial divided by m factorial divided by n minus m factorial. Okay. Some references that I used, the video on the negative binomial distribution by JB Statistics, and then sort of referring back, and also, since it's related to the geometric distribution, sort of my previous video with Wolfram-Cloud on geometric. I have 2 of them, and then also JB Statistics on the geometric distribution. Okay. So the first thing, if I'm looking at the full distribution, I'm going to do sort of what I did in this and sort of find expressions for the mean and the variance and the kurtosis and the skewness, and do a simulation. So play around with Wolfram on this. Okay. So I'm going to, first thing we should just check is that, if we have the right uh, probabilities, then if I add up all the probabilities, they should be 1. Okay. So we said uh, the binomial of x minus 1 comma r minus 1 comes in. The probability of success is raised to the r for r successes. The failure probability, 1 minus p, gets raised to the x minus r. And then I need at least, since I'm looking for r successes, I need at least r tries. So my summation starts at r and goes to infinity. And I can just, Mathematica is pretty smart. I can just ask it to do that, and it does it, and it gives me a 1. Okay. And then I'm going to ask Mathematica to get the mean for me, and then I'm going to sort of see what I can do to some extent without Mathematica or with less help from Mathematica, and then let it do its thing once I'm confident now I know how to do something. Okay. But here we are, sort of the same sum, except I'm throwing in an x in there, and that will give me the mean. Sort of what am I expecting, sort of on average, for the number of tries to get the r successes. So so this is how many tries to get r successes, and it comes out to be r on p. And that makes sense. In the geometric case, where I was only looking for 1 success, it was 1 on p. And now we're just sort of multiplying that by r. I want r successes. It's going to take me r over p. Okay. Now I want to start doing like central moments. I want to get the difference between x and the mean squared and cubed and to the 4th, these sort of central moments. And the first one is the variance. And now I'm going to try to do what I can sort of with less Mathematica, not just let it do it sort of blindly and spit out an answer, but let me think to see what I know how to do. So the variance be x, which is the number of tries, minus r on p, that is the mean. So I'm subtracting the mean and squaring that. So that's my normal way to get a variance. And then here I've replaced the binomial just with the corresponding factorials, x minus 1 factorial on x minus r factorial and r minus 1 factorial, and p raised to the r. And for some tricks I want to apply later on, I have replaced 1 minus p with a y. And then at the end, I will set y equal to 1 minus p. So that is that. So I took away the sum, but this is just a term. And then I want to, I had a sum that started with R. Where was that? My sum started with R, and I want my sum to start with 0. So I'm introducing, we're going to replace my x, which started at R, with a variable that's n plus R, so that when x was R, n was 0. So I just asked Mathematica to substitute that in for me. So it didn't affect the p. I'll just make these entered. So it didn't affect the p to the r. The x became n plus r. The y is now raised to n, so that sort of simplified that. This became a little more complicated, n plus r minus 1 factorial. This just became n factorial. This became r minus 1 factorial. Okay, so that is just a change in variable. Now, to the sort of hint here is we're sort of seeing this y raised to the n divided by and an n factorial in the bottom. There are other n's, but that's a sum we know how to do. That's the exponential. So I want to play around with the other ends that I'm finding, and then try to get it to where I can actually do the sum. So one thing I'm going to do is this n here in this, I have this square term to get the variance. I'm going to replace that n with y and the derivative with respect to y. So if I have, here's my y dependence, it's y to the n. If I take a derivative of that with respect to y, I get an n. It's just a simple power law, power rule. So I get an n times y to the n minus 1. And then if I multiply by y, I'm back to my y to the n. So this, I can replace this factor of n and think of it, get it in the end by having y d and then a derivative with respect to y and multiplied by y. Okay, so that's how I'm going to deal with this n. And then this other n that's hanging around that I want to get rid of, or not get rid of, but manipulate in a way, is I'm going to represent it. This is a factorial. Generalization of factorial is the gamma function. There is an integral representation of a gamma function, which is just the integral from 0 to infinity of t raised to the n plus r minus 1 times the exponential of minus t dt. So that is an expression for this factorial. And now I have my p to the r, I have my r minus 1 factorial, I have the square term, which is now y dy plus r minus rp squared. I'm going to have replacing this up here with an integral of my gamma function integral. And then I have y to the n factorial, and then I had t to the n plus r minus 1. So I'm going to bring out the part that doesn't depend on n outside, and then I'm going to have a part that does depend on n inside. So I split up my t's. And then I have, here's my stuff that depends on n now. And I can sum that from n equals 0 to infinity. That is just the exponential of ty. And so now in terms of t, I have t raised to the r minus 1, the exponential of minus t that was from my original gamma. When I sum this on n, that was e to the ty. So there it is. There, minus t minus y is ty. And I'm integrating that. And so I let Mathematica do that for me. And it gives me 1 minus y to the r. It gives me gamma of r, which is r minus 1 factorial. So that is canceling the r minus 1 factorial that was there previously. And so now I have all of this then simplified. After I do that integral, I have a p to the r, that's still around, and a 1 minus y to the r in the denominator. So there's that. And then I have my weird dy plus r minus r on p raised to the 2 acting on it. So here's that acting on, so I need that stuff acting on p over 1 minus y raised to the r. And so I've got to take my derivatives with respect to y and then make my substitution of y equals 1 minus p. Okay. So here's where I called my weird, I didn't have a name for these things, so I just called them BOP for no good reason. So here's my first uh, execution of this. So I have y d dy plus r minus r divided by p raised to some power. And actually, other moments, this is in particular because it's squared, is the variance. But if I did cubed, it would be the third central moment. If I did four, it'd be the fourth central moment. And I am going to do that. So my first one here is I call BOP. That is acting on uh, P on over 1 minus y raised to the r. And I'm taking, here's d is my derivative in Mathematica. And I'm taking the derivative with respect to y and multiplying it by y, and then adding r minus r on p, and that gets multiplied by that function. So I just let Mathematica have its way, and I call that BOP. So that was a single derivative. Now I played the same game on uh, BOP. I took that same sort of action and applied it to BOP. So that is related to the second central moment. I did it a third time. So I just keep taking this operator, which includes a differentiation, a derivative on, and so there is my BOP3, and then here is my BOP4. So those are all in there in my second central moment, the variance, my third central moment, which will be related to the skewness, and my fourth central moment, which will be related to the kurtosis. Okay. So now I have left the replacement of y going back to its original 1 minus p. So I'm taking BOP2, the second moment, and I get a sort of a known result. R times 1 minus p on p squared is the variance. And now I'm going back to the original x minus r to the p squared, the binomial. If I just let Wolfram do it all for me, yes, so we agree. So here I take what I call BOP3 and make my substitution and simplification, and I get an answer. And then I go back to the original sum and say, what if I just let Mathematica do it all for me? And we agree. There's a p squared, there's a 2, and then there's a minus 3, all in p cubed. Okay, so this is the third central moment. And then here is my fourth central moment. And then here is Mathematica's. And they sort of made it, I don't know, they expressed it in terms of a hypergeometric. And I'm absolutely, completely believe that it's true, but it's not necessarily as simple as it could be. This looks a little bit easier to me than that, because I'd have to look up what a hypergeometric means to do that. Okay, but anyway, but the other ones all agreed, so I certainly believe these two are equivalent. All right. The skewness is the third central moment divided by the second central moment raised to the 3/2. So this sort of like scales it so that it's more of a in sort of has some like invariance, and it doesn't depend, say, it's like a unitless quantity. And so there's an expression for the skewness. I just called it SK. I am taking, and that was 3/2 to the 3/2. The kurtosis is the fourth central moment divided by the second central moment squared, again, sort of getting rid of units. And I called it Ku for kurtosis. So we have relatively simple expressions in P and R. And now I'm going to run a simulation and then see how these and and do those calculations for my simulation and compare it to the theoretical results. Okay, so I'm going to have 10,000 samples. I have a list of samples. I needed an R and a P. I chose 3. This is sort of in my mind like I won't call it maybe a success, maybe, but like maybe a 3 strikes and you're out. I'm done. If if my P is the probability of a strike, and then I have 3 strikes, I will be done. So that's just me making it some sense of it in my mind. Okay, so I'm just saying here's my values of P and R that I'm going to use in my simulation. I'm looping over 10,000 samples. I'm going to count, I'm calling it, as I say, like I'm going to count them as, going to call them strikes. So I start with no strikes, and I have sort of, if I'm using a baseball analogy, maybe I should call this swing. How many swings, or I just called it tries, how many tries and how many successes, but I called it a strike. Okay, so while the number of strikes is less than 3, I'm not out. I get my random number uniformly distributed between 0 and 1. And if my random number is less than P, then I increment my number of strikes. I always increment my number of my swings, my tries. And then if I get out of my while loop, I'm going to append the samples, the count to my samples. Okay. Should have. Takes a little while because it is 10,000 and there's a while loop in there. So this is black while it's running, and then when it stops being black, then I'll know it was done. And then I'll be able to calculate the mean of my samples. Mathematica loves to give me things as rational fractions, so I slip in an n in there to make sure it's gives me a numerical value. Still running. And then I'm going to do the variance. I'm going to, once I get the variance, I'm going to take my second moment and put in specifically an R of 3 and a P of 1/6 and compare. I did stop running, good. My mean was around 18, which makes sense because it was it was R on P. It was 3 divided by 1/6. So that 6 is in the denominator. The denominator swings around to the numerator. 6 times 3, 18. That's expected. Okay. What is for my simulation? What is the variance? I'm getting of the order of 90. Before I had 88, now I have 90. Previous simulation. Now, what if I take my second moment, which above I called CM2, and that is, so the prediction is 90, the simulation giving pretty much 90, so that's nice. What's the simulated skewness? 1.14, I think it was 1.17 a second ago, and then what was it? 1.15. What was the kurtosis of the simulation? 4.78, And with putting in the R and the P in the expression above, I'm getting 5. So these are all of the same ballpark. The kurtosis is always going to be the toughest one to sort of duplicate simulation-wise because it's got the highest moment. So it is the most sort of, I don't know, tail probing of the measures. Okay, I decided I would make a histogram of the simulation in the PDF style of the histogram. So the PDF is sort of scales it both sort of vertically and horizontally so that it's not dependent on uh, bin width, and it's not dependent too much on the number of samples. So this is the nicest version of the histogram for comparing to if you had a mathematical function you wanted to compare it to. Okay. And then I am going to look at a box and whiskers plot with outliers. And so here are all the outliers, and you expect a lot of outliers. Again, it's an extension of the sort of geometric distribution. And sort of a normal distribution goes off as like, exponential of minus x squared. The the geometric only goes off like 1 on x or something. So it has a fatter tail, and so more outliers. So we see here the outliers. I attempted to see, I had in the geometric, because geometric series is so easy, you can sort of start it and end it anywhere and get a closed expression for it. Now, I didn't see any way myself how to do sort of partial sums. Like I was doing a lot of manipulation to make my sum an exponential, and then I knew how to do it. But I didn't know how to really do anything truncated wise. But I thought, let's see if Mathematica is smart enough to figure something out. So I sort of summed my probability up to some number of steps or tries and set it equal to 1/2 to see if I could see how many tries in terms of R and P to get up to M. And it was just giving me, it's just sort of saying, I can't do that. The methods I solve by, no. So I just wanted to give it a whirl to see if it could do it. It's not giving me anything nice like it did for geometric, but geometric is particularly simple. Okay, that's what I wanted to show you in this one. Again, mostly playing with Wolfram Mathematica, working with the negative binomial distribution, getting the various statistical measures, the mean, the variance, the skewness, the kurtosis, doing a simulation and seeing if our simulation and our theoretical predictions agree, and they did for the most part. Okay, thanks for your attention.